Hello, everyone. Thank you for coming back to my channel. And this is promoting safety engineering. That's what we do: process safety, technical safety, health and safety talks, that kind of stuff. That's what we do on this channel. And yeah, I know I've been away for a while. I've been away, you know, uh, life is happening. So sorry, I'll try to be a bit more consistent, but now I'm here. So today we're going to talk about process safety fundamentals, and this is something very, very key. It's an initiative from IOGP, that's International Association of Oil and Gas Producers, and it talks to about 10 rules that have been curated over 10 years that we as process that we could roll out on our sites, on our oil and gas sites, to reduce incidents that are related with process safety. So I would delve deeper into it. There are 10 of them, and these are all their logos. Stop when the unexpected occurs. Control your ignition sources. There are a couple of them, and I'll explain each one of them, and I will break them down with examples. I'll try to make it not too long. My videos could be a bit long, but I would explain what each one means and how you can roll it out on site. And I'll now give a spiel of how management can also push this on various oil and gas sites. So the it's a group of this was done mainly with the front line workers in place. So it's different from the 14 PSM, that's from OSHA, process safety management rules. Is different from that. This is more frontline workers, how they can actually, how the guy who's turning the valves, how the person who's running maintenance, how they can actually bring process safety to the front line, to their day-to-day activities. So it's to reduce, ultimately eliminate fatal and high severity high severity incidents that happen in high severity issues that happen in sites. So it's very, very easy to apply. Frontline workers, simple, broken down to your tasks, your day-to-day tasks, very proactive, and you kind of get a clearer picture of what process safety is all about. Not just having risk assessments, having HAZOPs, having PHAs, but this is for the frontline workers, what you can actually do on sites to reduce your incidents. So it's very different from life-saving rules. Life-saving rules also from IOGP. That's I said it earlier, International Association of Oil and Gas Producers. But this is more focused on process safety, fires, explosions, stuff that kills 3, 4, 5 people. Life saving is more health and safety focused, more focused on making sure you are safe when you're carrying out these activities by doing by doing the right things. So I'll have another video on LSRs, that's life saving rules, and I'll break those down also for you. So yeah, so how were these process safety fundamentals developed? So it was IOGP taking a group of incidents that happened over 10 years between 2007 and 2017, and taking those and actually going down to the root causes. What actually caused this incidents? There were 56 process safety events and 128 people lost their lives. And all the wisdom that was gotten from those 56 events were distilled into this 10 rules, or these 10 fundamentals. So they were developed data driven to reduce and eliminate high severity process safety events. And this was a bit of just a data set of 10 years. So, simple, clear icons, easy to understand for individuals. It's very, very good to know them and to apply them when you're out there carrying out your day-to-day tasks in your facilities. So, yep. And now also, so 128 people lost their lives to in this incident, and 9%, and out of those 128 people, just 9% of those people were not linked to this 10 process safety fundamentals. So 91% of the people that died, which would be about maybe slightly over 100, would all be related to these 10 PSFs. That if any of them, any of these process safety fundamentals was carried out, probably we would not have lost those lives. So I'll jump in. So these are the 10 of them. And I will break each one of them down. You can see their names: safe isolation, walk the line, apply procedures, that kind of stuff, sustain barriers, control ignition sources. So I'll break down each one, and I would give you examples of how that can, how we can actually apply them. So the first is we respect hazards. You're working on an oil and gas facility, or you're processing complex chemicals. You need to understand that these chemicals are very, very, some of them are very, very toxic. You have H2S hazards. You have just normal chemical hazards, that stuff that you're not supposed to breathe. Phosgene, they're just a long list of them. And you want to be able to respect those hazards because, hey, you're adding pressure, you're adding lots of heat to them, you're taking them to temperatures over 100 Celsius, 200 Celsius. You are keeping them in pressures over, 10 bar, 1,000, so 1,000 PA. So you want to make sure that, you respect that process. So improve our understanding of process safety hazards at our location. We have them through toolbox talks. We have risk assessments. We want to enlighten people about this process safety hazards. Also be vigilant about potential impacts of uncontrolled process safety hazards. You have to watch those. And then discuss process safety hazards before starting a task. Any task, you want to break open a flange, you want to start up a pump, you want to clear out a strainer. Be aware of the hazards that arise from that task. And also bring process safety hazards to be included in activity risk assessments. So this is the first one. We respect hazards, meaning, you don't want that complacency of we're just walking, we're just getting, you've worked there over 10 years, on a site over 10 years. There's a tendency to become really relaxed and look at it like, hey, stuff can never happen. But we have facilities that have been operating for 20 years, and then one day stuff goes boom, unfortunately. So we want you to always come to work with that mindset that I'm working in a hazardous environment and I need to know that and have that at the back of my mind when I come to work. An example is you're doing a hydro test on a line, and while you're doing that, you do a job hazard analysis, and you notice that one of the clamps during your hydro test is loose, and it's not hold. It's one of the clamps to hold your pipes in place is loose, and stuff is shaking or vibrating. You're having vibration hazards. You can actually stop that job and look to have it fixed, because it could lead to a potential rupture, because when you're hydro testing some lines, you go to very high pressures. Also, another scenario is a vessel that contained hydrogen sulfide. You're having H2S in a vessel, and then you just do a basic ventilation. You open it up, you don't purge it out, you don't try to ensure that do some gas testing. You don't treat it as a hazardous atmosphere, and you don't do a gas test, and a worker goes into that place and unfortunately succumbs to H2S. So you need to understand those hazards, that, hey, maybe we have H2S here. Maybe we need to actually come with our gas testing equipment, or you clean a tank that probably there was benzene. Benzene is hazardous, and you believe it's empty, but you don't treat it as a hazardous environment, and you go close to that tank and you're performing some hot work, and you have vapors igniting from that place. So that's also another. You should have done your gas tests in those areas. So process safety hazards. It's important to understand this process safety hazards at our facilities and be aware of the harm they could cause if we lose control of them. So don't get really normal with the risk. Don't look at this risk that, hey, I've done this 100 times. It's the same old routine work. Yes, it's the same old routine work, but stuff can still go wrong. So it's easy to become desensitized to these hazards. So when you're starting a task, do a risk assessment, a hazard assessment, and think of stuff that people don't normally think about and that could go wrong, and put controls in place. So your teams are supposed to be alert for risk assessments that do not cover all the process safety risks. And how can we make sure that these hazards during our day-to-day work are eliminated? So that's the first one. We respect hazards. Now, also, this slide deck was gotten directly from IOGP, so you can just Google IOGP process safety fundamentals, and you'd have the slide deck. So the second one is we apply procedures. Procedures. This is very, very key in the process safety world. We use operating and maintenance procedures even if we are familiar with the task. We're supposed to use our procedures. That's why we have them written out. That's why we have them made over and all updated over a couple of years, because stuff might have changed in the plans. You go on maybe you're on 3 days or a week of days, and then you go on vacation, and you come back next week and you don't know that some work has happened and they've added a valve there. And you come in saying, oh, this is the usual day-to-day task, let me just run it normally. And you're not aware that stuff has changed. So when stuff changes in the plant, it's part of the MOC process to capture that you need to update the procedure. So always make sure you have your procedures on lockdown, that you have them, you know them, and you're following them step by step when you're carrying out a task. Also, discuss key steps with a critical procedure before starting it. They are critical procedures, they are emergency procedures. You need to discuss those steps. Pause before key steps and check readiness. So as you're carrying out the task, you see a step that this is key, pause and check if you're ready to go ahead with that task. Then also, if there's any issue when you're applying maybe you see that, hey, there's something here that shouldn't be here. Stop the task, inform your supervisor, do some investigation, and if you don't feel safe, make sure you don't go ahead with it. And also become very familiar and practice emergency procedures. You should carry out your drills, as much as you can. Now, a couple of examples are, you want to start a gas unit, maybe a compressor, without following the checklist, because you just want to save time. Every time we're always in that mindset to hey, we need to do stuff quickly. But then, you didn't pick up that a drain valve was left open, and then the gas escapes and ignites. So you should check your startup list and follow your procedures. And if you did that, probably that drain valve would have been caught in the procedure, and they would have the procedure would have said ensure that valve is closed. So that's a scenario. Also, you're starting let's say a distillation unit without using the established up-to-date startup checklist, because stuff is updated regularly, and then you want to resume procedure. But you didn't check your pump alignments. You didn't check that all your valves are properly lined up. One valve may be left open or closed, and this triggers an emergency shutdown. So you don't rely on past experience, especially when it's a critical or emergency procedure. You need to keep that at the back of your mind. So how do we do this? How do we apply procedures? Verify firstly that your procedures are up to date, and they are effective and easy to use. You don't want to combine 10 steps into one line. Start the pump. You need to explain it, break it down step by step. Follow up if concerns about a procedure are raised. Become familiar with the plant, its equipment, its procedures. You've gone on a 3-month sabbatical, you're back. And you want to make sure that you get back into things with knowing everything that has changed, and keep aware and informed of emergency procedures. This is very key, because this is when stuff wants to go south, and you need to be very aware of your emergency response procedures by carrying out drills and that kind of stuff. So that's the second one. Apply your procedures. The third is sustain your barriers. Now, this is so process safety. This is very process safety, because our barriers are our safeguards. They're our safeguards we have on sites. Uh, our trips, our fire and gas detection, our making sure our pump seals are good, our containment is good. We don't want to have loss of containment. So, different things, barriers, your fireproofing, making sure that they're good. So there's software, there's hardware barriers. Software barriers are stuff like, your uh, control system, like your Delta V system. You want to make sure that's good software, and then the hardware, the actual physical stuff, like stuff I've mentioned before, and your human barriers. So we're supposed to evaluate how attacks could impact process safety barriers. Yes, because sometimes we want to bypass some trips, but we're supposed to actually see how badly it could affect the system. We're supposed to speak up when barriers don't feel adequate. Do we? Like, hey, maybe we don't have enough safeguards for this, for this task we want to come out. We want to break that we want to do. We want to break a flange open. We want to isolate a pump. We don't have a double block and bleed. We're supposed to speak up when we feel these barriers are not adequate. Perform our roles in maintaining barrier health. We want to make sure that all our barriers are healthy. That's part of what we need to do when we are carrying out tasks, and use an approval process for operations with degraded barriers. So you have a vessel that's that probably one of the drain valves is not properly holding, it's not properly isolating. You want to look at that, at maybe this is not good, and have an approval process that this barrier is degraded. Or let's say you have a line corrosion. It's corroded. It's a badly corroded line. You want to have a process for actually operating that line and having additional barriers in place. So we're supposed to sustain our barriers. Now, a couple of examples. A sensor, a pressure sensor, a pressure indicator is faulty, and you don't fix it. You just want to bypass it. But whereas that sensor is supposed to trip on high pressure, it's supposed to trip a compressor or a pump on high pressure. But because it's faulty, you want to bypass it, and why not just fix it? Because here you bypass it, the pressure goes above the operating limits, and it doesn't trip what it's supposed to trip, and you have a surge, and this incident could have been avoided by replacing that sensor and not doing the work, right? Or you're so overwhelmed with a lot of work on sites. You don't have enough manpower to inspect all your PSVs, your statutory inspections, your yearly inspections of your PSVs. You leave them, and you don't run a couple of inspections on one of them or a few of them, because you don't want the downtime. But then you're operating and that PSV sticks. That PSV is actually a mechanical barrier to protect you when you're going above when you're going to over pressure. That PSV is supposed to lift, but the PSV sticks because you didn't run your maintenance on it. And you have line ruptures, you have vessel ruptures, you have loss of containment. So that's just that PSV could have helped to relieve stuff to the right place, instead of and so those are like barrier samples of barriers. There are lots and tons of barriers we could go into, but that's just a few. So we should have that at the back of our mind, that our barriers should be healthy. And how do we sustain barriers? We should know that all our barriers at each location. From probably you could have a bow tie for that location and look at all the barriers you have in place. That's why having your bow ties is very critical. And how does this affect my work if these barriers are bypassed? Ensure that these processes are in place and you have necessary resources to test and maintain these barriers, and make sure that these barriers are effective. They are actually doing what they're supposed to do, and they're tested to make sure that their functionality is 100% as much as you can. So that's on sustaining your barriers. So that's the, I don't know, is that the third one? Then with the fourth is stay within your operating limits. This is so important. We have so many times that operators ignore, or you see this pressure spike, you see this temperature spike or temperature dip, and you just ignore it. That, oh, okay, this, yes, is abnormal, but hey, we have this every other week and it's becoming normal. No, we should respect the hazard and stay with it, because guess what? Your system was designed to actually, there's your operating pressure and there's your operating temperatures, and you are supposed to actually stay within those limits, because that's what your system is designed for. We have different types of steel, different types of metal, stainless steel, that we use to build our facilities, and some of them, there's only a limit. There's a limit to what they can take. So make sure we discuss and use approved operating limits. If we go outside the operating limits, we're supposed to carry out an investigation. It's not only when we have loss of containment that we should be worried. If we're going constantly, so many incidents have happened, and I need to reiterate this. So many incidents have happened because of going outside of operating limits and having it normalized. So also we escalate to where we cannot walk within operating limits. Hey, this pump is pushing out too much, or we don't have a means to step down the pressure, and we can't walk within operating limits. We should be worried. These alarms keep on going off. This trip keeps on tripping this pump. Why is that happening? So we need to actually have a clear response and clear response time to respond when all this, because a lot of things happen. This alarm goes, and within a minute after the alarm goes, we have a catastrophic event. There needs to be time, process safety time, factored into the design, that when the alarm goes, we still have about 10-15 minutes of operations to actually respond to it, or even 30 minutes. So we should design our systems with that in mind. It varies. For process safety, time varies, depend on different companies and different facilities, based on what you're operating. Also, obtain formal approval before changing operating limits. This should be like a full MOC. You're changing your operating limits, you're increasing pressure, you're increasing your temperature, you're increasing flow. We should actually carry out some serious engineering investigations before changing our operating limits, and also confirm that potential for overpressure from temporary pressure sources has been addressed, because you could have overpressure, and you want to make sure that your system can handle that. So a couple of examples is, you're doing a cold startup and you see a temperature spike in a column. Instead of letting it exceed the limits, just because you want to hit your production targets, because every time we're pushing for production, you know, maybe we should reduce the feed rate, the flow rate, and check what's happening, because this prevents thermal degradation and a dangerous overpressure events. A scenario also could be, you're increasing throughput, you're pushing a lot because you want to meet aggressive production targets, and then your pressure and temperature, they spike what the system is designed for. Your operating pressure, your design pressure, you're almost exceeding those, and then you start having thermal stress, and then a flange fails. You have a flammable release because you are operating outside your safe operating limits, or a heater is run above design temperature to boost throughput. You're increasing that heater temperature, and then the tubes in the heater fails, and you have to shut down. That's you're going, because you want to produce more, but you end up shutting down your site for a couple of days just to fix a tube rupture. you know so there are things, these are all staying within operating limits. And how do we stay? We should have a document saying all our safe operating limits and our key process variables, and all the frontline workers should know them, and stay within them. Also, regularly check for personnel knowledge and skills. Are they knowledgeable about it? We run our trainings, we run our assurance tasks to make sure that our operators know what they're doing. Then also systematically investigate excursions outside our safe operating limits. We're supposed to investigate those excursions. We're supposed to. And so when those happen, that you have those pressure spikes, those trips, actually carry out an investigation to see what's the root cause, and it could be something a lot more sinister than you're aware of. And demonstrate that through these decisions that cost, production, or schedule does not override safety, because safety involves human lives. So there's no matter the amount of production targets you want to hit, or cost, money, cost you want to save, that should override safety. We don't want to push that message out. We need to stay within operating limits. Our operators need to know this. The next is we maintain safe isolation. That's the fifth. I think everyone needs to understand how important and critical safe isolation is. This is so key. And, you want to have your positive isolation. You want to make sure that stuff is staying inside the pipes. We use isolation plans for the specific tasks. So based on up-to-date information, we want to make sure that we have all our isolation plans in place. We are to raise isolation concerns before the task starts. So you want to work on a pump, and stuff is still operating, or it's not, or we have other equipment still operating, even if that pump is off, or even if they are not operating. We want to challenge the isolation plan. Do we have our double block and bleeds in place? Are we blind flanging it? Do we, and our valves, our isolation valves, are they holding? We want to go there and make sure that we can actually isolate. And we then, with your double block and bleeds, or you have a bleed in place, to check if there's residual pressure in the system, or the processed material. We want to make sure that before breaking that containment, breaking that flange, opening that isolation valve, or that strainer, before opening it or going into that vessel, we want to make sure that there's no residual pressure. Everything has been drained out, and there's no energy in there. There's no stored energy. So we'll want to also monitor the integrity of isolation. So we should regularly stop and reassess if there's any change that in our task that could affect our isolation integrity. Confirm leak tightness. We're testing visually. We're testing with gas detection before, during, and after reinstating equipment. You want to make sure that we are checking to make sure that we don't have any leaks. This is very, very key, because we're dealing with hazardous chemicals. We're dealing with oil and gas. We're dealing with H2S that could, high ppms of H2S that could put, unfortunately, God forbid, people to sleep really, really quickly. So we want to make sure we maintain safe isolation. And what are a couple of samples or examples? So we're working on a steam line, and you want to cut open a steam line. Before starting that operation, verify that the line is fully depressurized, because steam expands very, very, very aggressively. You want to make sure that that line is fully depressurized. There's no steam in it. It's locked. It's tagged. Your loader procedures. Are you locking out? Are you tagging out? Because hey, you're working on this section of the plant, and then someone is working on another part, and hey, you believe, hey, I closed the valve, but you didn't lock it. But what if the person working on another side of the plant believes that this valve that it's 500 meters away needs to be open, and he opens the valve and it affects you where you're working. So if you've locked it out, the person would know, hey, someone is actually working there, maybe I shouldn't manipulate this valve. Or they would come meet you and say, hey, what are you doing? Try to find out why that lock is in place. You're using it to save your life. So, make sure that the valves are locked, they're tagged on both upstream and downstream isolation points. And this actually prevents releases, or this could prevent the release of steam. Or, a maintenance crew is working on a double block and bleed system. They want to use a double block and bleed to isolate, and they only close one side of the double block and bleed. And then, we have back pressure when a line is opened downstream, and you have a loss of containment. The crew, they suffer burns, or whatever is in that line spills on them. Or it could be a hydrocarbon line. And a lot of old systems, they don't have double block and bleeds in place, and you only use a single valve that is could be passing. That valve could be, you use that single valve as your isolation, and it could be passing. And that hydrocarbon, you have hydrocarbon in the line, and that sprays everyone, and you have an ignition. Or it could be H2S gas, gets everywhere, high ppm, you know. So those are a couple of examples. And so how do you maintain safe isolation? Isolation practice at your location, verify its effectiveness. Look at your P&IDs. Look at walk your line and make sure that this is holding, and check. You can check their temperature guns. You could just use to check maybe if it's steam. Hey, do we still have steam in there? You use your temperature gun to check. Or some people even just touch it if it's not too hot. Touch the line. Have various isolations in place to make sure that, hey, this is safe. It could be something that it's gas. You want to test it if it's holding, and then respond and follow up if isolation concerns are raised. You don't have positive isolation, you should be worried. Regularly check that those performing isolations are effectively trained and supported. We can say this over and over again. Training, assurance, verification, it cannot be underestimated. Thank you so much. Then the sixth is walk the line. So we use up to date. This is once you're an operator, you need to honestly constantly walk your line. This needs to be done, and this is done with your P&IDs. So are your P&IDs up to date? You have a change here. Has it been effected in your P&IDs? And make sure that the site, the plants, is accurately reflects everything that's installed. You have a drain valve here. You have another valve there. You have a temperature trip here. Stuff is being added, over time. You want to make sure that you walk the line before starting any task, and physically confirm that the system is ready for the intended activity. Your valves are lined up, and your relief devices, your bursting disc, your pressure, your PSVs, they are all the upstream and downstream valves of your PSVs are open to make sure that they can operate. Alert supervision to identify documentation and readiness. So you see something wrong with your P&IDs or your cause and effects matrix, and you alert your supervisors that, hey, this is wrong and we need to change this. There should be a system that should ensure escalation of whatever frontline workers see. And a couple of examples here are, a blind, you want to start a line, or you want to start flowing through a line, and there was a blind flange, a flange. The line was blind flanged before, and that you didn't know that blind flange was removed, and you go in there and you start up, or maybe some people were actually working and on that line, and they removed the blind flange, and you didn't know that blind flange was removed, and you start the line and you have a leak of hydrocarbons. A walk the line could have caught that, or a bypass valve. You're lining up your pumps, and you find out a bypass valve was left open. You could, during your walk the line, that can actually catch it. Or you do a turnaround and you start up a unit without a walk the line after your turnaround, and then a temporary blind flange is missing, or a spectacle blind was removed, and from that drain line, and then you have your leak from that line, and then you have a fire. So we want to make sure that we're working the line before we start a lot of these tasks. It's very, very key. And so how do we do that? Regularly confirm that our PSI, process safety information, our PNIDs, PFDs, our hidden material balance, so many, that they are accurate and up to date. There needs to be, because stuff is changing in the site. So, and then we discuss this walk the line issues with all the frontline workers. And if you're a supervisor, make sure that you follow up with concerns that are raised, or if you're a leader. And even if the frontline workers themselves should follow through and make sure that some of these concerns are actually handled. Check that systems are in good condition and correctly set up each time we start up or make a significant change in their use. So that's on walk the line. Then that's, I think, the sixth. The seventh is we control ignition sources. Very, very, very key. We do our hazardous area classification, make sure we have the right equipment in each area of our hazardous area classification, that each equipment is rated and designed for that hazardous environment that we're putting it in its zone 1, zone 2. I should actually do a video on hazardous area classification. I think that would be cool. So we identify, eliminate, or control the full range of potential ignition sources during task risk assessments and during job preparation and execution. This is very, very key. We are using the right tools. We are using intrinsically safe equipment. Minimize and challenge ignition sources even in non-hazardous areas, because hey, we could have gas clouds that travel and cause ignitions, and eliminate ignition sources when we're breaking containment. So you're breaking containment, you need to make sure that, sometimes you have people having hot work in some other areas. Even if it has to be close by, maybe they need to do it they need to build a containment, like a little shed, to make sure that all sparks are contained. There's so many ways. You need to make sure that cars that are passing, whatever vehicles you have in that area, that they can handle not releasing sparks that could cause ignition. So all this, it's all control ignition sources. This is very, very key. A couple of examples also. I said I was going to give example for each one. Is you want to weld a bracket on a pipeline or on a pipe rack. You want to weld a bracket on it to keep it in place. And the fire watch says, hey, let's have one final gas check. Or maybe we're supposed to have continuous gas monitoring and detects hydrocarbon vapors when you want to do that welding. That work should be postponed, because we've had lots of stuff that's happened that way. That work should be immediately postponed, because guess what? The area has not been purged and isolated. Go back, do a purge, and make sure you're properly isolating it to ensure that we don't have flammable gas or toxic gas in that area. Or another example is you want to do some hot work in a near tank that's could vent flammable vapors. they are not maybe it's not constantly venting. It vents every 30 minutes, every hour. But guess what? Stuff happening that you're not aware of on in that tank. Maybe because some other people are working, are doing some stuff downstream that could actually affect that tank, makes the tank vent a lot more. So make sure that you have functional gas detection in that area, because hey, guess what? You don't have that gas detection, or maybe it's not functioning properly, and you know you're doing hot work nearby, you have an explosion. So make sure you're constantly testing for gas and eliminating hot work as much as you can. And if you can't, then you have your hot permits to work, looking at everything that could cause an ignition. So that's control ignition sources. Then the next, okay, a couple of how do we control ignition sources? Regularly check that personnel understand the full range of potential ignition sources, and control work risk assessments to evaluate the potential for flammable hazards, even inside and outside those areas that are classified on the area classification drawing, your hazardous area classification. Make sure that you're eliminating flammable hazards, and report defects in electrical equipment. Electrical equipment bring sparks, and that could also ignite flammable gas. So make sure that any, you have wires that are frayed, you have equipment that are faulty, electrical equipment. You want to make sure that you have controls in place to eliminate those ignition sources. So that's the seventh. And now we go to the eighth. We could be here forever. MOC, recognize change. This is very, very, very key. Over time, over every year, your plant is changing. You're having so many changes. I call it, the plant is gradually becoming a Frankenstein. Your your facility is changing every day. You're adding parts and parts and parts to it, and you're adding valves, you're adding vessels, you're adding drains, you're adding pipe racks. Stuff has changed. Are you capturing each change in an MOC? We're supposed to actually have an MOC process in place to capture, risk assess every change that we're doing, and see what could trigger unhealthy or unsafe conditions. So we are supposed to discuss these changes, involve various disciplines that to actually have that could actually have different views from us, to actually look into those changes. Discuss and seek advice on change that occurs gradually over time. So review the MOC process for guidance on what triggers an MOC. Have that MOC process in place. This is so key, because hey, you had a valve here, you had a trip here, you had a vessel here, you had a pump here, and you're not properly capturing it in all the documentation, in your P&IDs, in your PFDs, in your plot plans, in your safe operating limit documentation. You need to actually capture everything and make sure that all the documents that relates to that change are updated. So a simple example is, it could be a chemical that you change. You usually use maybe caustic, and you have that, you change that, or you use a type of sealant, and you change that sealant because maybe you find one that works better, or is cheaper for facility operations, and you're always trying to bring down costs, but no one captures that change. And then that's change, that new sealant that you're using, reacts with some of the chemicals you are processing. So it could even react. Some could react with oxygen, and then you have fire or whatever happens based on that, or you have a loss of containment, you have a leak because stuff has reacted. If you did a proper MOC, you would have actually investigated that new chemical you're using, and you should have, it would have been caught that this does not work well with our operations. Or let's say you have a block valve installed on a line and you don't properly MOC it, and it doesn't show up on your P&ID, and then you're doing a shutdown activity and you miss that you should actually isolate or close that block valve, and then you flood the vessel with gas or with H2S. So those are recognized change examples. And how do we recognize change? This I've already so verify that your system identification and MOC process are in place and working effectively. Ensure that workforce personnel and management are trained, because sometimes they may not know that this is a change that we should actually log or actually MOC. And teams can review their local MOC process for guidance on what triggers MOC processes and discuss examples. So everyone should be aware of what should be MOC'd and actually run it through it. So thanks. That's we've come to 9. Stop if the unexpected occurs. This is simple. You're working and you have a signal that tells you stuff is not going as planned. Stop, pause, ask questions. When signals, you're seeing that the stuff is not going well, stop, ask questions. Stop, tell your supervisor, I'm not comfortable with doing this because this, and this have happened. So, what are some of the samples I have? I could, the million and one. You're doing your walkarounds or your rounds in a facility that has a lot of H2S, and you hear a H2S alarm, or you're carrying out an activity and you hear an H2S alarm that's not related to your activity. Maybe you need to stop and say, hey, where's this H2S alarm and where is it coming from? Maybe I need to get out of here. Don't be so used to get so comfortable with walking through these conditions that are not normal, or operations identify a pinhole leak. Maybe you should stop and immediately roll back what you're doing, or you're having a pigging event. You're doing a pigging activity, and you see a pressure spike, and you say, hey, maybe I should just continue. Maybe you should stop, because it could indicate that that you're going to have a line rupture. So, or you want to operate a pump, or you're operating a pump and you hear a knocking noise. Probably the pump is cavitating or has mechanical misalignment, and you just continue doing what you're doing, and the pump actually fails, and you release a flammable liquid everywhere. You should have caught this. You should stop if this is happening around where you're working. So stop if the unexpected occurs. And so, people are supposed to reevaluate a task if it's not going as planned. That's normal. Stop and reevaluate. Communicate to frontline workers. Management needs to let frontline workers know that they can pause and seek guidance if an activity is not going as planned. Pausing or stopping a task, it may feel inconvenient at the time, but remember that if you keep on going on with that activity and stuff gets out of control, you could have an incident. So you're supposed to keep people safe, and you're also saving your employers a lot of money. And finally, we have watch for weak signals. Now, what are weak signals? This is like SOL excursions, stuff that indicates that things are not right, but they're so tiny, you just want to sweep it under the rug. And hey, no, a lot of those, have you seen the Swiss cheese model? Maybe I need to do a video on that. If a lot of these holes line up in the Swiss cheese model, lots of tiny weak signals could all combine and become a great signal, and which stuff goes boom and it's too late. So you need to proactively look for indicators or signals that suggest future problems. Speak up about potential issues, even if we're not sure they're important. You just have this minor, you're going 2, 3, 4, 5 kPa above pressure. It's normal, but hey, it might not be normal. You're having this constant leaks from this pump, tiny leaks, but hey, they are weak signals, and it's your site speaking to you that it's actually telling you that, hey, I need some love, I need some maintenance. So we should persistently explore the causes of changing indicators or unusual situations. Now, a simple example is what I said earlier. You notice a pump a seal is leaking very small amounts of hydrocarbon during startup, after once you start up that pump, it leaks for like 5-10 minutes and then kind of seals off. We have those situations that happen. It seals up and the leak stops after 10 minutes or 15 minutes of operating. Instead of accepting it as normal that, hey, in 10 minutes this is gonna stop. No, it's not normal. Check the root cause. It might be a shaft that's misaligned or a seal that's failing. And, before that seal fails catastrophically, because it could do that 10, 20 times over the course of 2 years, and then eventually it fails catastrophically. So investigate it. Observe small recurring gas alarms. That's another example. You have this gas alarms that keep on going, and you say, oh, it's just a compressor leak, it just leaks, and it's been happening over weeks. Your plant is talking to you. These are weak signals. Don't have it normalized. Make sure that you're constantly checking. Maybe we're at peak load, and any loss of containment would at peak load could indicate a large flammable cloud from that compressor. Or you're having nuisance alarms. Oh, it's just a nuisance alarm. Just turn it off. Just turn it off, because you're having minor leaks, and you continue producing, and eventually you have a major leak. Those are all samples of weak signals that we should be worried about and look out for. And how do we watch for weak signals? Be alert to weak signals. Respond proactively when the signals are raised. Even if the signals seem weak, small, or important, there's a video from they're talking about chronic unease. I think it's from Shell. You can Google it, chronic unease, and watch that video. It's talking about weak signals. They're to be discussed and evaluated. And weak signals, there could be a good opportunity to avoid a future accidents. And so it's important that we are persistently exploring them to understand the causes and eliminating those root causes. So these are 10 steps that management could do to roll out this process safety fundamentals. I've spoken on the 10 of them, and these are another 10 ways management could roll them out. So first is leadership commitment. Is our leadership actually actively involved in this? Secure visible support from senior management to prioritize this process safety events. Process safety is very, very key, and communicates the importance of these 10 process safety fundamentals. Leadership should show full support of that. Then also, second is assess current practices. Do gap analysis to see, okay, where is your process safety management right now, and how are we getting to rolling out all these 10 PSFs. Identify areas that need improvements. Like, are we supposed to improve our procedures? Are we supposed to update them? Are we supposed to train? Look at your current practices. Do you have your safe operating limits in a document? Are we maintaining our barriers? Check all your present activities, practices, and make sure that there's always room for improvement. The third is develop implementation plan. Do we have an implementation plan? That's very, very key. There should be a clear roadmap on how we're going to roll them out, with timelines and responsibilities on hitting those targets, and then we focus on those 10 PSFs. The next is training and awareness. We can flog this to death. Train frontline workers. Train. Verification, assurance. Make sure that they are trained on all the 10 PSFs and how to identify them. And, we have our toolbox talks. We have our safety moments that should always speak to these PSFs with real incidents when we're discussing. And then the fifth is integrate into our work processes. So all these PSFs, we integrate them with our lockout tagout procedures, our gas testing procedures, our hot work permits. Use these work checks to ensure safety barriers are in place before the tasks begin. Then the next is leverage technology. Of course, we have so much technology these days. There's cameras everywhere. There's AI. We could leverage all this gas testing, visual testing, fire detection systems to see if we're having violations, if there are PPE violations. Are the workers using their PPEs? Are they unsafe conditions? Our gas detection, fixed gas detection, are they picking up any hazards, any flammable gas or toxic gas? And incorporate AI into it. And then we have also monitor and verify. We need to have our KPIs. We need to pull in all the information that helps us be comfortable, have these dashboards that speak to, hey, are we on point? Are we monitoring? Are we verifying that everything is good? And we to conduct regular audits and inspections to ensure that we are in compliance. Then the next is encourage reporting and learning. We need to do that. Everyone needs to be able to be comfortable to report without feeling that they're going to be penalized by management. Reports and learn. Foster an open culture for workers to raise concerns about hazards or barriers. Share lessons from previous incidents, videos to talk about them. Then continuous improvement. Continuous improvement, this is so key. It's part of our MOCs. We're constantly making sure that this little things, this little changes, this training, this awareness, we're constantly improving. We want to foster that kind of environment that we're taking back feedback from the workers. We're incorporating that feedback into our daily tasks. We're analyzing data to make sure that, hey, we're constantly looking for how to improve our trends or how to minimize incidents. Update procedures, training based on findings to sustain improvements, and then also engage stakeholders. Make sure everyone is engaged. Top management, middle management, frontline workers. Make sure everyone is collaborating. We have constantly contractors, suppliers, regulators who are not part of our of a company. We are working with them, collaborating with them to adopt all these PSFs and share the information. So those are just 10 easy steps that management could use to roll out PSFs. This is for frontline workers. How should you use it? Have your toolbox talks, safety meetings, do your pre-job planning, make sure it's detailed, all your risk assessments, and then your last minute risk assessments. Check, are there any line or fire hazards or ignition sources we didn't identify? Last minute, post job reviews. After you finish the job, look what went well, what didn't go well, how could we do things better? Observations and walkabouts. This is so great. Do you see anyone performing work where PSF is relevant when you're doing your walkabouts or observations? And then let them know about it. Intervene. Don't say, oh yes, they're not doing it. Are they following it? Yes. If they're not, intervene and teach as much as you can. And if you don't feel comfortable, stop the work if a PSF is not being followed. So those are ways that the frontline workers can. This is for frontline workers. The first one was for management, this frontline workers. And then, this is the IOGP website. This is the link. You can go there and get a lot more information. So thank you very much. If you like the video, subscribe to the channel. Thank you. God bless.